this video, we're going to look at some chemical equations. So let's start off in chemistry. Physical and chemical changes involve a change in state, or dissolving, because dissolving isn't really one of our three states. We'll talk about that in a bit. Chemical changes involve the creation of a new substance with unique properties. And there are 4 signs that a chemical change has occurred, and one rule of thumb to guide you in these decisions if a chemical change has occurred. So here are our 4 signs in no particular order. Sign number 1, there is a change in color. So if you direct your attention down to this picture, it says you've spilled bleach and your blue shirt has now gone white. There is a change in color. Next one, the formation of a gas. So if you put 2 things together and you smell something, that is the formation of a gas. 3, formation of a solid. This is you're pouring 2 liquids together and something solid appears within the solution, something that won't dissolve. That is a solid, also called a precipitate. And lastly, there's a change in energy. So there's a couple of things that can happen. Either energy is given off in the reaction, like this burning log. That is called an exothermic reaction. It is hot. Or the opposite, say for instance, you crumple up in phys ed one of those packages that you're supposed to put on your body after you get hurt and it gets cold. That is known as an endothermic reaction. And there is a rule of thumb that says if the thing is hard to reverse, then it is a chemical change. So any of the ones we just talked about that are hard to bring back to the original substances, those would be considered chemical changes. So what we want to focus on here would be chemical equations, and because these are used to represent these 4 changes. So here's an example. This is pretty much everything you're going to see in a chemical equation. Coefficients, there's some arrows, states, reactants, products. Let's talk more about that. So first, let's talk about the substances. So when you do a reaction, often you have at least a couple of reactants. I've written 2, and then you put an arrow. By the way, you can have 1 reactant, 4 reactants, whatever. And the reaction occurs, and you could have 1 product, you could have many products. So this is essentially a chemical equation. Next thing would be the symbols that you put into your chemical equation. So if something is in the solid state, you use a little S. If something appears in the liquid state, like water, you put a little L by it. And if something smells, it's a gas, you put a little G. And like we mentioned earlier, you can have something that gets dissolved in water, like you have table salt, you put it in water. It doesn't vanish, it just changes into the aqueous state, AQ. That means it has dissolved. Now 3, the law of conservation of mass is going to come into play here, and that just says atoms are neither created or destroyed in a chemical reaction, only rearranged. So why don't we take a quick interlude of a video here where we're going to see one of these reactions occur, and then we can come back and talk about it. So as you saw in that video, some orange powder was lit on fire. There was actually 1 gram of orange powder at the start of that reaction, and then there was a bunch of green powder at the end. Well, guess how many grams of green powder were created? Yeah, you guessed it, 1 gram, because the law of conservation of mass. Sure, it might have just been changed around, but whatever mass you have before reaction is what mass you have after reaction. Now this plays into chemical equations because they don't often come with this idea in hand. That's why we need to balance these equations. And that essentially means to get the same atoms on both sides of an arrow, both sides of a reaction, so that we can conserve our mass. So let's look at some balancing of chemical equations. Here is a pretty simple equation for you. So aluminum sulfide breaks down into aluminum and sulfur. Now I've got only a couple of tips to this stuff because there really isn't a set number of rules. There isn't like I could tell you to do A, B, and C and everything will always work out perfectly. No, you got to just kind of play around with some things and see if you can get it to balance. So the first tip I would say would be to count the atoms of each element on each side of our arrow. It's essentially what I'm saying here. So if we look over here, we've got 2 aluminums right there, and over here we only have 1. So the aluminums are not balanced. At the same time, we have 3 sulfurs over there, and we only have 1 sulfur there, so those sulfurs are not balanced. So that's we've got an idea of a couple of atoms that are not balanced. Some of them might start off balanced, and that's fine. So what we're going to do is we're going to use coefficients. We're going to place them in front of the compounds as needed. So here's where the balancing comes. So coefficients are just numbers, like 2, 3, 25, whatever. And we're going to use these numbers to help us get the same atoms on either side of our arrows. So getting back to the original aluminum, we said that we have 2 aluminums right here. So if we want to get 2 aluminums on the other side of our equation, we put a 2 in front of it. And with our sulfur, we said we have 3 here and 1 here. We want to get 3 on both sides. What we're going to do is we'll put a 3 in front of the sulfur. So if you count it up here now, we've got 2 aluminums and 2 aluminums, and 3 sulfurs and 3 sulfurs, and every atom is balanced. Let's take a look at a couple more examples. Okay, here is another one. There we go. So when you look at this, hopefully you notice that neither the carbon or the hydrogen is balanced on either side. Again, on our left side of the arrow, we've got 5 carbons, and here we only have 1 carbon. So what should we put in front of carbon to balance it? A 5. Very good. Now keep in mind this is multiplication, not addition. So now we've got to think about our hydrogens. We have 7 here, and we have a 2 there, so not an even number. So there's a couple of different ways we can go about this. One easy way is just to use something called the half method. So we ask ourselves, what number times 2 will give us 7? And if you're thinking, you realize it's 3.5. And this one is actually done. You can actually take another step and go through and multiply every coefficient by 2, doubling it just to get it up to be like whole numbers, and that's been said. So like I said, we double everything. So if there's like a pretend 1 in front, we make that a 2. This would become a 10, and this would become a 7. And the half method works exactly the same. So either are really acceptable. Let's take a look at another one. Aluminum chloride breaks down into aluminum and chlorine gas. So if you look at the aluminums, we have 1 on either side of our arrows, so they're actually balanced to start. But then if we look a little further, we've got 3 chlorines on the left side of the arrow and only 2 chlorines on the right side of the arrow. So it's almost like a little math. So it's like saying you had 1/2 and you were trying to add it to 1/3. Well, you need a common denominator, right? That's fraction way. Another way to think about this is to say, well, what's 2 times 3? Well, that equals 6. So what I'm telling you is that we want to get 6 chlorines on either side of our equation. So let's start with the left side. If we've already got 2 here, what do we want to put in front of a big compound? 2. Now that does change the number of alumins, but we'll come back to that in a second. So as it stands right now, we have 6, 2 times 3 chlorines on the left side. Over to the right side, we've already got 2. So what number do we want to put in front to give us 6? Hopefully you thought it was 3, because that is correct. So 3 times 2 gives you 6 chlorines. Now, like I said, we're not finished because we put a 2 in front of this. We need to balance the aluminums. And yeah, we're just going to simply put a 2 in front of that. And now that gives us 2 aluminums. So everything's balanced. 2 aluminums and 6 chlorines. Okay, in this one we've got aluminum nitrate plus sodium chloride giving us sodium nitrate. And lastly, aluminum chloride. Okay, so what's special about this one is that we have a nitrate involved here, an NO3 and an NO3. So this is a good place to start. What I like to think about is to say, okay, well, how many nitrates have we got on this left side? And it really comes down to this number outside. It tells me that we have 3 nitrates on this left side. Over on this right side here, we only have 1 of these NO3s. There's no subscript outside. So if we have 3 over here, and we have 1 over here, probably the first thing I want to do is I want to get 3 nitrates on this right side. So all I'm going to do is I'm going to put a 3 in front. So my nitrates are now balanced. I have 3 nitrates there, and I have 3 nitrates there. So that is good. But by adding that 3 in front of the compound, it applies to both numbers. So it now says I have 3 sodiums. So looking back to the left-hand side here, I only have 1 sodium right there. So what do I need to do to get 3? Well, I'm going to put a 3 in front of that. Now that has once again changed what we've done, because that not only applies to that Na, it also applies to that Cl. So we have 3 Cls here. Oh, look at that. We have 3 Cls on that side. So when something like that happens, you probably did it correctly. Notice so far through these examples, we've only used small numbers. 2s and 3s are mostly what you're going to be using to balance these. So one last one we're going to see come up. This is called a combustion reaction. some balls, an everyday reaction. That's how we get that's how our cars work. They combust. They make energy out of these hydrocarbons. So a hydrocarbon is something that starts off this one, and that's where I think I should start. So looking at this, how many carbons do we have? We have 5. How many do we have there? We have 1. So hopefully you're thinking, well, I should probably go ahead and put a 5 in front of that carbon dioxide. Now, I know that 5 applies to the oxygen, but you might notice that we have oxygen and a couple of different compounds here. So I'm actually going to come back to that. And that's my tip. When you've got hydrogens and oxygens, try to do them last. So let's go to the hydrogen next. We've got 12 of them here. And over on this side, we have 2. So let's ask ourselves, what's 2 times, 12 times, 12. All right, so if we've got 12 on one side, let me just start over here. And we've got 2 on this side. I guess a little division would work. 12 divided by 2 gives us a 6. Let's see if I'm right. Yeah, I'm right. Okay, so that's what we've done here. So 6 times 2 gives us 12 hydrogens. So the hydrogens are balanced. But we've got oxygens all over the place now. How many oxygens do we have here? Well, don't say 5 because we have 5 times 2. We actually have 10 oxygens. And here we have 6 times 1 gives us 6 oxygens. So adding 10 and 6 together gives us 16. So we need to get 16 oxygens over on this side. Well, good news, we already have 2. What's 16 divided by 2? That should be 8. So another way to think about it is 8 times 2 gives us 16. And we have done it. We have balanced this one. So now go forth and try some of the balancing equation homework. Please take up your answers.